Start off. Hmm. I didn't know people are celebrating Christmas also. Now you can celebrate, nothing wrong with that. But then at least you should get to eat a plum cake. So if there's no plum cake, then what is the point of Christmas? When we were in school, na, our school had a lot of Christian teachers. Most of them are Anglo-Indian, so it was celebrated in a good way. And we used to get 4 days holidays. That's why we used to love Christmas because you get 4 days holidays. That was one. And second thing, na, so during the school, right, they used to distribute us plum cake also. And I think I was very small, fourth or fifth standard, I guess. I used to watch a lot of cartoons. In all these cartoons, there is one common theme. Santa Claus comes in the night and gives you a gift and goes, isn't it? So I and my sister, now one day we decided, yeah, we'll sit there, we will wait for the Santa Claus to come. So I and my sister were sitting with sticks and we are waiting there. This guy will come, we will beat him right and left and take all the gifts. Well, if he's going to come anyway, so why to leave him? Na? That was the plan. We sat for the full night and we slept off on the stairs only. I think morning we are on the bed. Mom took us and kept it on the bed. We didn't come. So yeah. And then later I realized when you close the entire house and seal the house, how will you enter inside? The next year I told my mom, open the doors, keep the doors open, let him come. This time we'll catch him. So my mom is like, Santa Claus won't come, thief will come and will take everything away. So
Merry
we
Christmas,
used to
sir.
have kya karne Merry Christmas. You're not even giving me any cake. And I didn't even give you a holiday.
Sir, extra questions on Christmas.
Extra questions
They're
on
giving
Christmas.
us the gift of learning, sir.
ये तो देख तो देन ग्रेट ना नेक्स्ट वीक तो न्यू ईयर है उसका भी छुट्टी नहीं है देन
All okay, sir.
That's fine, sir.
नहीं सीरियसली यू गाइस वांट अ हॉलिडे नेक्स्ट थर्सडे क्या नेक्स्ट थर्सडे इज न्यू ईयर आई गेस
No, sir, it's fine.
It's fine, sir.
चलो ठीक है आई वाज नॉट प्लानिंग टू गिव एनीवे बट आई शुड मेक यू फील हैप्पी ना लाइक ओ सर वाज रेडी टू गिव वो इंपॉर्टेंट है
As long as there is good food, I'm fine.
That's what they do to when they want to torture someone or something. They make you think that you have a choice, but you don't have a choice.
Yeah, वो होता है ना कभी कभी your mom will talk to you and you will say mama मैं जा रहा हूँ your mom is like तू जाना है तो तू जा मैं देखता हूँ it feels like your mom is giving a choice तो जाना है जाओ that is the tone your mom gives you right कभी observe किया you feel like there is a choice your mom is saying you want you can go or you don't want to go but there is only one answer for that question if you go you're going to get right and left from me so that way let's see anyways Utsa, will you be taking a test today? What test, Utsa? I think you're confusing me with someone else. I teach physics. So let's see. So last thing what we're doing was this projected area thing. So let's go a little more on this projected area. Now, this is quite an important concept. Like I said, this will come 6 times. So what's the projected area? So it is an area which will make an open surface into a closed one. Meaning, if you take some random amoeba shape like this, right? So look at this argument. Let's say if you take this random amoeba shape, which is completely closed, this is a whole closed shape. If you look at the pressure acting on this, so we'll have a pressure acting on this disk, the pressure acting on this curve. Do you agree that net force on this cylinder will be 0? Just imagine if you take a massless closed random shape and if you keep it in the atmosphere, it will not going to move, right? because the total pressure acting from every direction will cancel out. That means from here I can make an argument. So the force acting on this random curved surface plus force acting on this disk must be equal and opposite. So the force acting on this random curved surface and the force acting on this disk must be equal. So force on the curved surface plus force on the flat disk must be 0. Is that argument making sense? Since the total force was 0, if you take any small area, that force and the remaining area must have equal and opposite force. So therefore, we can make a simple statement. The force on the curved surface is the pressure into projected area. So the disk here is the projected area. I'll give you some examples. But there's only one problem with this. This will work only when pressure is constant. If pressure is variable, you can't use this. Example. So let's say if you have some random surface like this, or if you take even a hemisphere, or if you take a cone also. For all these shapes, this is the projected area. So when you keep this area, that entire curve becomes a closed figure. This is the projected area. So force acting on all of them will be the pressure P into pi r square. Is this making sense, everyone? So it doesn't matter what kind of shape you take. You keep this disk, and on top of it, you keep any shape you want. The pressure force will be always same. Because the total force must be 0. So the force on the curve plus force on the disk must be 0. So therefore, force on the disk is equal to force on the curve. Is that clear, everyone? Now I'll give you one more shape. You guys tell me what is the answer for this. What if I take only half cone? Right? What if you take an half cone where this is 2r and this is height h? Right? And the pressure is acting on this curved surface. I hope you're able to see the shape of it is. So that's an half cone. What is the force acting on the half cone? This is the center. So if I ask you this question, find the force acting on the left half of the cone. So you cut the cone vertically. What is the force on this? Yeah, give me the answer. Na? You can get a value. You'll get a good value. You'll get a proper value there. Find the force on the half cone. So instead of taking a full cone, I cut it in half. So you'll get only a half cone here. And the pressure will be acting at an angle. Find the net force acting on this curved surface. I hope you can visualize how it is. A 3D shape. Huh? So the pressure is acting in all directions. Like near हो गया. That's not the complete answer. नहीं Srihari. Again, go back to the definition of projected area. What is projected area? An area which will make an open surface into a closed figure. I want to make this into a completely closed figure. So if you want to make this into what is a closed figure? You can't enter inside, right? If you want to make this a closed figure, what do I need to do? I need to put a disk at the bottom and I need to put a triangle at the side. Is that making sense? I need to close this with a disk at the bottom. So I'll just shade it with green. And I need to also close it with a triangle here. Now it becomes a closed figure. Then what is the force acting on this? So on this, the force will be pressure. It's the pressure is V. The area of that half disk, which is pi into r square by 2. On this, the force will be pressure into area of the triangle, half into base into height. So the force on the curve will be force on these two surfaces, which is P into RH I cap minus P into pi r square by 2 j cap. Are you getting this? Because देखो ना, this force is not horizontal. This force is at an angle. It will have a horizontal component. It will have a vertical component. So for this thing, there are two projected areas. Matlab, you have to get that entire thing to become a closed figure. So you need to put an half disk at the bottom and you need to keep a triangle at the right side. Then it becomes a closed figure. I hope you're getting what's the projected area. So it's in a vector form. So projected area simply, you need to put an area such that the figure becomes a closed figure. Remember like that. So by putting an half disk at the bottom and putting a triangle on the right hand side, this half cone becomes a closed figure. Are you sure what we did? Any doubts on this? So that's so projected area. Keep this in mind. This will keep coming up multiple times. Next one. But remember, projected area ka one problem is the pressure has to be constant, or else you can't use it. Let's say we have a hemisphere. Density of the liquid is rho. The height is h. Outside the pressure is P naught. This is a solid hemisphere of radius r. Now, because of the liquid, there will be pressure acting on the surface. But the problem here, this pressure is not constant. Find the force acting on the curved surface due to the liquid.
So is the bottom welded?
It doesn't make a difference. So be careful. Here, pressure is P is equal to P naught plus rho gx. So P is not constant. You can't use projected area. So remember when to use, but also remember the conditions it is valid. You can't use it wherever you want. So how do we handle this? Try na Srihari, get some answer and then ask na. In the exam, whom is going to come and tell you each and everything? Try. Nere Arya. How did you get an answer without H in the thing? So you're saying it won't matter what is the depth. I r square rho g. So minus centromass क्यों ले रहे हैं God? Centromass, that thing is for a sheets, isn't it? That was an half disk. It was a sheet. How can you use it for a 3D structure? Let's see. One thing to do, we can integrate. It goes quite lengthy, but there's a much faster way to do. Listen. So this shape now, when you take this solid hemisphere, just look at the liquid on top of the hemisphere. This was height h. So if I draw FBD of the liquid on top of the hemisphere, so can I say this thing? So this is how it would look. So what is a free body diagram? So from the top, we have atmosphere P naught into pi r square. Then your own weight mg is acting. And then here, this pressure, I don't know what is this exactly, but this will be the force due to the hemisphere on the liquid. So this is the force due to the curved surface. By Newton's third law, this will be the same force due to the liquid on the hemisphere. Do you guys agree with that? Are you getting the argument? The total force acting on the curved surface is simply, I don't care what is this, the simply all this weight which is acting on top of the surface, this is responsible for this pressure, isn't it? Is that making sense? The total weight acting on top of the hemisphere is responsible for the force acting on the curved surface. Are you sure? That's it. You're done with one step. There is no need to integrate anything. So F curved will be P naught into pi r square. What is the mass of this? That thing is a cylinder minus hemisphere. So this is radius r. That will be density into volume. Volume will be pi r square h minus 2 by 3 pi r cube. That is the volume of the hemisphere. Rho v volume into g. That's your answer. This term here is the volume of the liquid above the hemisphere. There's no need to integrate this thing. Is that making sense, everyone? Sure with this? So this is a very useful statement. Meaning, let's say someone gives you some random shape like this. And if they tell you, right, there is a fluid acting on top of it like this. So the force acting on this curved surface, so if you look at this, the force acting on that curved surface, so whatever force that is acting on that curved surface is simply weight of this liquid and upper se pressure into area of this thing, isn't it? So this will only give you the vertical component though. So the vertical force due to this upper curve is nothing but mg plus p naught into area. Is this clear, everyone? So whenever someone puts something in a liquid and they ask you what is the force acting on the surface, you need not integrate. You just simply understand all the weight of the water on top of it must be responsible for the force on the curved surface, and you're done. All clear with this? So you can avoid integration without that, but you still decided to do integration. You can do that. It'll work. So we take a ring. Hope you remember how to do this. We already did this twice. At an angle theta, we will take this thing as r d theta. This height will be r sin theta. तो यहाँ पे pressure will be P naught plus rho g h minus r sin theta. That will be the pressure, and the area. Now, there are multiple problems here. This pressure will act like this. So this force will be P naught, P into dA. Uska vertical component, that would be PdA sine theta. So force will be integral PdA sine theta ka integral. So this will be P naught plus rho g h minus r sine theta, and the area will be 2 pi r cos theta r d theta sine theta. Limits will go from 0 to 90. And if you do this, you will get the answer. Getting it, you will get the answer. But there, this is much faster and easier. All clear with this? Let's see one more. I will leave it there. So if anyone wants, you can check how did I take the elements. So basically on this area, the force is acting at an angle. So we should take its vertical component. You can't even directly do P into dA. So we have a U-shaped container like this. This is filled with two different liquids. Density rho. And this is 2 rho. This height is L. And this is L. This is also L, and this is also L. Normally, the liquids can't stay like this because there are different densities, the liquid will move. So the moment you started accelerating this is possible. So when this container accelerates with A, the liquids will be exactly of same height. Find the acceleration if the liquids remain in equilibrium with respect to container. To maintain this kind of a system, what is the acceleration of the container? Because if the container is at rest, the 2 rho will dominate, it will push the liquid, rho will rise and 2 rho will come down. Find A if the liquids are at rest with respect to the container. Not on the ground frame, with respect to container. Let's get this. G by 3. Okay, let's see. That looks like right over here. Right, Arya. Right, Samyak. It's mostly an NLM problem. Try, I'll give a minute more. Let's see. Nesh Hari. So let's look at these 2 points, okay? Let's call this thing point A and let's call this thing point B. Just draw the FBD of that horizontal thing. So if you like the FBD of this horizontal thing, this is rho, this is 2 rho. So here this will be pressure of A into area. This will be pressure of B into area, and this is acceleration A. So PA into area minus PB into area is equal to mass into acceleration. But what is PA? PA will be nothing but P naught plus 2 rho GL. PB will be P naught plus rho GL. into area. Mass will be, now remember this thing is L and this thing is also L. 2 rho area length L plus rho area length L into acceleration. Area into length will give you volume. Volume into rho will give you the mass. Area will cancel on both the sides. P naught will cancel here. We'll end up with rho GL is equal to 3 rho acceleration. L is also here. A is equal to G by 3. Check. Simple free body diagram. So this horizontal liquid in this content is accelerating with A because of the difference in pressure on both the sides. So PA minus PB into area must be equal to mass of this horizontal into acceleration. And what is PA? Now we know pressure changes only vertically here. Remember, horizontal acceleration will not affect in the vertical direction. So PA will be P naught plus rho GH, 2 rho GH, and PB is P naught plus rho GH. Easy? It's a good question. This will be a proper mains level question. Yeah. All clear with this? Any doubts on this? Clear, na, Tanishka? Vedika? Yashvi? Clear? Yashvi? Yashvi, are you there? Clear? Let's see one more. This is another standard result. You should remember. We have a test tube. Filled with liquid. This thing is rotating with omega. This is rho. This is x is equal to 0. This is x is equal to L. So at a distance x here, so neglect any gravity here. Find the difference in pressure minus px minus p axis. So I want you to find the pressure at some point here, which is px, and this is your pressure at the axis. If they say it is an open cylinder, then it will be P naught. If I don't say anything, it will be Px only. This 14A result you should remember. Using this, we have a U-shaped container which is rotating with omega. This is L by 4 and this is 3L by 4.
So is the cross-section area given in the
It doesn't
A
matter.
part?
This is H1 and this is H2. Find H2 minus H1. Both the questions are related. Gravity is there. Anyone remembers we did something like this, the 14A somewhere before. Anyone remembers where? This question, yeah. There is a rod here, mass m length L, rotating with omega. Find the tension at a distance x. We took an element at a distance dx and then we solved the whole stuff. Idea is similar. There I called it tension in a circular motion rod. Here it is a liquid. Try. Get the first one. I'll give you a minute or two and we'll see the second one. Right, Arya. Go ahead with the next one. Rho omega square pi r square. What is r? Utsa, I didn't give you any radius. Yes, right, Samya. I think you got that extra pi r square that is not required. Let's see. So at a distance x, take a thin slice dx. So if you draw the FBD of this thin slice, then we have pressure from the left-hand side, pressure into area. Pressure from the right-hand side, P plus dP into area. I hope you remember this. We always assume pressure is increasing with x. The signs will take care of it. And the centrifugal force will be dm omega square x. Because that small piece is rotating in a circle of radius x. So here PA will cancel. So dP into area is equal to dm into omega square x. So dP into area, dm will be density of the liquid, area of cross section into thickness. That is your dm. Area will cancel on both the sides. We get dP is equal to rho omega square x dx. Integrate on both sides. This will go from 0 to x. Be careful at here the pressure is p axis and this is px. So the difference in pressure px minus p axis is rho omega square x square by 2. So this will always give you the difference in pressure between the axis and the point. You cannot use this from anywhere to anywhere. You always have to use this formula from the axis. Clear? It's a standard result. This itself is a mains question. Find the pressure at so and so point. Right over here. Right, Ishman. All clear with this? Any doubts on this page? So can I try the question? Now try the B part. Right, Samya. Now you are rotating this not from the center, but at L by 4 from the left-hand side. Find the difference in height. Right, Arya. Square L square by 2G नेरे होता. So how do you handle the B part? Remember, this is your axis. So consider this point as A, consider this point as B. This is L by 4 and this is 3L by 4. This was H2 and this was H1. So when you try to apply the formula, PA minus P axis is rho omega square x square, but x ka place mein we have L by 4 whole square by 2. Similarly, when you do, so you can't do between A and B directly, be careful. You always have to use the formula from the axis. So P axis will be rho omega square x square. Here x is the distance between the axis and point B. 3L by 4 whole square by 2. When you subtract them, you will get PB minus PA will be rho omega square by 2. That is 9 minus 1, 8 by 16. So that is L square by 2. But what is PB minus PA? This guy will be rho G H2 minus P naught minus rho G H1. There, you get H2 minus H1 is equal to omega square L square by 4G. Clear with this? Because when you're rotating, the centrifugal force is in the horizontal plane. It's not going to affect anything in the vertical direction. All clear with this? So check it out. So if you don't know the result for the first one, the second one you won't be able to do. So you need the first result, the difference in pressure in a rotating cylinder. Next one. Any doubts on this? Clear, na, Srihari? Rudran?
Sir, but the pressure is in vertical direction. So how can we equate it to horizontal direction?
What are we talking? Pressure is a scalar quantity. Pressure
Sir,
is
so there is
scalar. It
nothing
has
like
no direction. So pressure, if you go
Sir,
from
so
top or bottom, you're reaching the same point. The pressure must be same.
oh,
Na? Scalar quantities don't depend on direction. Next one. Let's say we have a square plate of side L. This is another standard model. So on the left hand side, we have liquid. So it's like a dam ka wall. So, and you're applying force F here at a distance y from the top. Density of the liquid is rho, gravity is present. So basically this wall is blocking the liquid. So a square plate of side L blocks a liquid of density rho. Right? So, and you started applying force at a distance y from the top. And external force F is applied at a distance y from the top. Find F and y for the plate to be in equilibrium. How much should you apply and where should you apply? If you apply wherever you want, the plate might rotate. Find F and y for equilibrium. Now you need to understand something here. If I look at the side view now, listen to this thing. Here the pressure is not constant. So when you're designing the walls of a dam, this is something which you have to take into account. The pressure as you go down, it keeps increasing more and more. This is how the pressure will be on a dam. So this will be P naught plus rho gx. So that means the lower part of the wall is experiencing more force compared to the upper part of the force. So when when they construct the walls of a dam, they have a very intuitive design. If you ever seen a dam, right, it looks like this. Do you know when is the dam more stable? When it is fully filled with water. The more the water in the dam, the more stable it becomes. Now think about that logically. Let's say you build a dam ka wall like this straight. What happens? As the water is getting filled up, the pressure is pushing the dam ka wall. The only one who's stopping the wall from moving ahead is the friction on the ground. And the friction will depend only on the mass of the wall. So if you just build a straight wall, the problem is you have to make the walls really heavy in order to balance the water cut dam. But look at this design. As you fill up the dam, the pressure on this bottom part starts increasing. As you go up, the pressure decreases. Now, because of this more pressure, you get more normal reaction, you'll get more friction. So the more water in the dam will increase the more pressure on the floor, that will increase more normal reaction and more friction. So the dam actually becomes more stable. Is that clear? So the only thing, so the walls will not move forward and backward, so they will remain at rest, they'll get fixed up. So generally dams become more stable as you fill up the water. That is the reason the design is like this, it's more curved. Anyway, so let's get this. So imagine it's a square plate. So find the force and the y. We'll not get into all that right now. We are simple people here. Right? When you're in mechanical engineering now, when you're in actual engineering, they'll teach you all that stuff. You'll have a lot more than just a shearing and longitudinal and everything. Could be Utsa, meaning
सर
I never did research on that. You can figure it out. Arya.
सर हमें F दिया है कि Y दिया है कि F कांस्टेंट रख के
तो
Y निकालना है.
ऐसा नहीं है. You both will get very unique values. You have to keep the thing in equilibrium. मतलब क्या? You can't move, you can't rotate. Nah, if you apply whatever you want, the plate will move. So it depends. So if you actually see now, there are all the dam walls are not like this. What I showed you is one thing. Later on, I'll show you. There are some dams, where they're built in the shape of an arc. They're vertical only, but they're like an arrow kind of thing. So yeah, there's nothing like there's a perfect equation. It depends on a lot of stuff. That's an interesting thing. Dam ka curvature. Let's see. First, let's find the force. That's an easy part. You have to integrate though, because as you go down, the pressure is increasing. You can get that rho L square. Near dimensions में match नहीं हो रहे यार. Yeah. I hope the question was clear. The problem here is as you keep going down, the pressure is increasing. So the force is not constant on every part of the wall. The lower part of the walls are experiencing more force compared to the upper part of the walls. And if you see the wall also I constructed, can you see this is more thicker here? So this thing serves the double purpose. It is more thick here, it is less thick here. I don't know, Mumbai में इतना बड़ा dams are somewhere close by, but if you ever been to Andhra Pradesh, right, Srisailam, Nagarjuna Sagar and all that, these are pretty huge ones. You clearly see that structure, like, right, Samir? Right, Arya. How to get the force part? See. Arya, Samyak, can you do if the density of the liquid is not constant? Let's say it is rho naught 1 plus x by h by x by L. Density of the liquid is rho naught 1 plus x by L. Means as you go deeper, the density is also increasing. Try for that and tell me what is the y for that.
From surface, right?
Surface. Now, listen, see. So when you go from the top at a distance x, we will take a thin strip dx. So on this thin strip, what are the forces acting? So this will be length L and that will be dx. So area of the thin strip will be length into dx. So we have force from inside, which is P naught plus rho gx, that is the pressure into area. And remember, there's an atmospheric pressure from outside also. There is a pressure from outside also, which is P naught into area. So basically, P naught will cancel on both the sides. So the net force, so force on each strip will be rho gx into dA, which is rho gx into LdX. So the force on the plate will be integral rho gl x dx from 0 to L. That is rho g L cube by 2. So this much force you are getting because of the liquid, and this must be equal to F external force if you want to be in equilibrium. Clear with this? If you don't apply this much force, the plate will move right or left. What about the torque? Now see, this thing is also rotating. If you take the torque on the strip, we are taking about the topmost point. What is the torque? Distance x into force on the strip. Again, remember, every strip will have different force, every strip will have different distance. That means the torque for each strip will also be different. So we have to integrate the torque due to each strip. This will be x into rho gx dA. That would be rho gx square, dA will be L dx. So the total torque on the plate will be rho gl integral x square dx, 0 to L. That is rho g L into L cube by 3. That is rho g L power 4 by 3. That is the torque on the plate. Clear with this? So now what you're trying to do, so on this plate, you are applying a force F somewhere here at a distance y. So the torque due to the external force is F into y. This must be equal to the torque due to the plate. But what is F? F we already calculated, rho g L cube by 2 into y must be equal to torque due to the plate, which is rho g L power 4 by 3. Therefore, y is equal to 2L by 3. So you should apply this much force if you want to keep the plate at rest. But if you apply this force wherever you want, the plate will rotate. So you need to apply this force at 2L by 3. It kind of makes sense actually. Because the lower parts are experiencing more force, the force must be slightly below the center of mass, isn't it? Are you clear with this? So you can't apply the force in the center. Please have a look at this. So I found the force on each strip and then we integrated the whole thing. 7L by 10. Yeah, that looks right. 7L by 10 and force कितना था 5 rho g L cube by 6. Okay, weird. आर्य एक बार चेक करो न्यूमरेटर फोर्स का पार्ट. Any doubts on this part, everyone? All clear with this? Clear, na, Anvita? What happened? Not well today? It's good. Or it is very cold. Or missing Christmas. Or people are angry because I took a class on Christmas. Then clear with this? Trishi, clear with this? Shaunak? Sudiksha? Sudiksha, clear? Sudiksha, are you there? Yeah. Great. So that is one thing. Let's see the next one. Barometer. So what is this barometer? So it's pretty useful to get the pressure. So consider a 1 meter long glass tube. Filled with mercury. And then invert this into a cup of mercury, into a trough of mercury. The trough is basically a bowl, basically, into a trough of mercury. And if we observe, the liquid level actually drops. Creating a vacuum at the top. So first thing what you do, you take a 1 meter long glass pipe. You fill this with mercury and you make sure there are no air bubbles inside. Hg, mercury. Then what you do, you invert this. You take a bowl of mercury and in that you keep it inverted like this. And what we observe, if you just leave it like that, you will notice the liquid level starts dropping automatically. You will notice this height becomes h. And here there is vacuum. Basically, once the liquid comes down, there's nothing to occupy. And at this point, because it is exposed to atmosphere, here the pressure is P naught. So now if you actually draw the FBD of the liquid column, so it is a mercurica cylinder. So on the top, the pressure is 0, so there is no force. At the bottom, it is P naught into area and your own weight mg, which is density of mercury, right, into density of mercury into area into height h. Since it is in equilibrium, P naught A is equal to rho mercury G in A into H into G. Area will cancel on both the sides. You end up with H is equal to P naught by rho GH, rho mercury into G. If you substitute the values, this thing comes out to around 76 centimeters. This is how actually it was derived. In that chemistry, when they say 76 centimeters of mercury is 1 atmosphere pressure, this is what it means. 1 atmosphere pressure can balance 76 centimeters of mercury column. Clear with this? So that was the meaning of it. Now, in this certain precautions in this experiment, there should be no air bubbles. Why? If you have air bubbles, you won't get vacuum on the top. And if you have vacuum on the top, then if you don't have vacuum, then the height won't be 76. If there are air bubbles, there is no vacuum at the top. Second thing, we don't use water. If we use water, there'll be a water vapor on the, because what happens, right? If you put water in a vacuum, it actually vaporizes. So you get a vapor pressure there. So water is a bad idea. If you use water, there'll be a vapor pressure. Basically, you'll get steam in that vacuum region.
So why doesn't mercury have vapor pressure?
It does not become into a liquid state like that. वो substance का है, I guess. It's not that volatile. Water, if you see, the molecular bonds are maybe more, they're more weaker. Mercury bonding is very strong. So surface tension we must have seen, na? It actually liquid gets cohesive forces are stronger.
Yeah. Sir, so there is equilibrium, but the constant is very, very low. Can we say that?
Maybe you can say there'll be very little pressure, maybe negligible. See, the same argument you can say, if you put a steel block in vacuum, why doesn't it vaporize? The bonds between steel bonds is more stronger, then they can go out. You guys know what is boiling point, right? Exactly. Listen, if you don't have an idea, I'll tell you a bit about it. कभी आपने observe किया? Take a glass of water, put water there, and put the plate on top of it and leave it. After 1 hour, when you go and see under the plate, you will find water droplets. Observe किया? Ever observe that? Observe that. You don't need to do anything. Just put a glass of water on top of it, put a glass ka plate and leave it there for an hour. Go and open the thing, you will find water on bottom of the plate. No heat, nothing is needed. Getting it? So the thing is, when you take a liquid surface, the molecules are not at rest. These molecules are moving randomly however they want. We will see this in thermodynamics. Now, when the molecules are moving randomly, what happens? The molecules who have more energy, some of them will start escaping the surface. Now, Getting it? So what will happen? If these are escaping, what will happen? All the high energetic molecules will keep going out. So the liquid actually cools down, right? And because the liquid is cooling down, it absorbs heat from the surrounding. So again, temperature will rise. Again, molecules will keep going. So if you just take a plate of water and keep it in your kitchen and leave it, by morning, all the water will vaporize. कभी observe किया? But if you put something, a lid on a container, now because water cannot escape, what will happen? The water will get stuck on the bottom of the plate. It will again condense and fall back. So molecules are going, they're coming back. Molecules are going and coming back. So eventually, right, you reach an equilibrium there. Are you clear with this? So now how fast the water will vaporize will depend on two things. So if you have a water there, if outside your pressure is P naught, so what is the air trying to do? The air is trying to push the molecule who wants to come out. So this molecule which is trying to come out, the atmosphere is trying to push you back. So if you have high temperature, molecules will escape more faster, so water will vaporize. Or you can do something else. If you decrease the pressure outside, P naught by 2, because the outside there is opposition is decreasing, even for low temperature, water molecules will go out. So water will start boiling even at low temperature. If you ever been to this, this Kedarnath trek and all these high places, right? Water will boil even at 50 degrees. Kabhi observe here? Water starts boiling. You put your hand, nothing happens. You feel normal. Now imagine the extreme case. When you remove the entire air outside, you create a vacuum. Now if you create a vacuum, there is no one to stop you. What do you think will happen? The moment you keep the water, the entire high energetic molecules will start escaping. So if you take water and throw in vacuum, you know what happens? If you take a glass of water and throw in the vacuum, all the molecules on the surface will vaporize. But because you are vaporizing, you need energy. So the inside part of this thing becomes an ice ball. So some part of the water becomes ice and the remaining part will vaporize. So if you take a human and throw them in space, you don't explode or anything. First thing, what happens? All the water that you have on your surface, in your eyeballs, in your tongue, everything, right, will just vaporize. And once the water vaporizes, to vaporize, you need energy, right? That comes from your own internal body. Your body will freeze. So if you throw someone into the space, they freeze to death.
Sir, but like why the water vapor?
It is the other way around. See, water vaporization matlab kya? High energetic molecules escaping the surface. If all the high energetic molecules escape, what you are left is only low energetic molecules. Matlab your temperature dropped. ऐसा सोचो ना, it's like in a class of 100 people, if you start removing all the people who scored more than 90 plus, the overall class average will start dropping. And the average kinetic energy is what we call as temperature.
Sir, so when we keep it in a open container, then it's the pressure which is stopping most of the molecules by like to not go out.
Yeah, but फिर भी there will be some molecules which will keep escaping. So liquid ka temperature will drop, but it will absorb heat from the surrounding. Again, you will regain the temperature. Again, they'll escape. So this process will keep going on.
That explains why hill station ki Maggie is good and
नहीं,
it's
कभी
cooked
ये
fast.
observe किया, like why it feels cool under a tree. Under a tree, right? Under the leaves, they do something called transpiration. पढ़ा school में? Under the leaves, they have these small pores where they're releasing, that little droplets of water. Or did you ever see this thing? Why the water in a pot is cool? Because some part of the water keeps vaporizing from that porous structure, so the overall thing becomes cool. Anyway, we will see in thermodynamics. I will teach you that. But chemistry, if you have surface chemistry, they'll teach you in more detailed. Clear with this? So the formula for this, so height of the liquid column will be pressure P naught by rho g. There, this is the formula you need to remember. So that is one way to make ice actually. If you do sudden expansion, right, it freezes to ice. That's what actually happens in your refrigerator and your AC. कभी सुना ये word? Sir, आपका AC में compressor खराब हो गया. Ever heard that term? Your AC का compressor was gone. So what happens in a refrigerator and AC, right? You compress, there is a coolant inside. कभी ये सुना आपके AC का gas leak हो गया. So inside there is a gas. right? Which is compressed and expanded suddenly. When you expand suddenly, right, it's an adiabatic expansion. It cools down. So that is the only process where we can do. And the same problem, when you go to these hill stations, right, cooking food becomes a problem actually. Maggie jaldi cook nahi hota hai na Arya. Cooking will always happen at a temperature, isn't it? If the water starts boiling at 60 degrees, your rice won't get cooked. It is just an illusion water boil over hai, but rice doesn't get cooked. So what we do now, we use a pressure cooker. Because of the pressure cooker ka that whistle, right, the water ka inside the water will boil at 150 degrees. That is the reason if you're cooking rice in a pressure cooker, it gets done in 10 minutes. If you cook normally, it will take half an hour. You're cooking the rice at a higher temperature. Anyway, so that's a little about that. So for mercury, this value will turn out to be H is equal to 10 power 5 by 13,600 into 9.8. That comes to around 76 centimeters of mercury column. If you do it for water, this is another reason why we don't use water. It's too much actually. 10 power 5, water ka density is 10 power 3, and this is 9.8. This thing comes roughly 10 meters. So who will take a 10-meter ka pipe and keep walking everywhere? So it's a bad idea. Clear with this? There. Take a break, come back by 9:40. We'll continue from here. Chalo, camps on everyone. Now, in this thing, right, the barometer, this experiment is actually famous for what? This experiment is actually famous for creating vacuum. So during this 1800s, now people used to think vacuum can be created only by devils. I don't know. They had their own logics and concepts. So they thought normally you cannot create vacuum on Earth. It was some kind of an evil thing. So this experiment actually became famous for the vacuum. No one actually cared about that pressure and all that stuff. So happens a lot. Now listen here. If we do something here, other scams on. So this is the barometer. And let's say this is the mercury thing. So let's say if I give you a question like this, let's say this is point A and this is point B. Tell me what happens if I make a hole at point A and what happens if I make a hole at point B? What do you guys think will happen if you make a hole at point A and a hole at point B?
There is surface tension there.
मेरे वो सब ignore करना. Don't bring new things which I didn't teach. तू भी ना. Where did I teach? So if you make hole at A, what will happen? The air will start rushing inside. So the pressure here will become P naught. So the vacuum will vanish and the liquid will go down. Others cams on. Advai, Ovya, Ishman, cams on. What if you make the hole at B? What do you think will happen if you make a hole at B? Ask yourself, what is the pressure here? P naught. So if you go up, let's say it is at a height x, the pressure here will be P naught minus rho gx. And outside the pressure is P naught. So air goes from where to where? Air goes from high pressure to low pressure. So if you make hole at point B, the mercury won't come out. Instead, the air will start entering inside. Right? So the air will enter inside from here. And now because this mercury, whatever is there, once the air enters, these bubbles will start going up. And once the bubbles go up, the vacuum goes off. End of the day, the liquid will still come down. Air enters inside, bubbles go up, and the liquids come down. So you don't get a fountain like this. Are you getting this? If you make a hole at point B, you won't get the liquid spilling out. Bubbles go up and liquid comes down. Clear with that? So basically, there is a high pressure here. So air goes from high pressure to low pressure. So that they can frame theoretical questions like this. Clear with this? Great. Let's see a question. So let's say we have a barometer. So when the pressure is P naught, let's say the height is 75 centimeters. Now, if you take this and keep it in an escalator or elevator, it's going up with acceleration, and let's say the pressure inside becomes 3P naught. And is observed, this height becomes 60 centimeters. Find the acceleration of the lift. So a barometer on the Earth's surface will give you 75 centimeters for a pressure of P naught. The same barometer, when you keep it in a lift and you accelerate up with A, it gives you 60 centimeters. The hole made at B, yeah, Utsa. Matlab, the thing is, you know what? The moment the air enters inside, once the liquid comes to here, then maybe a little might leak out, but first thing the air will rush inside. Actually, if you make a very small hole, later on we will see there is something called surface tension. Nothing happens. The liquid will not let the air come inside also if you make the hole too small. But that's a concept for some other day. Let's get this thing. Easy one. We'll again encounter these kind of questions in gravitation. Seven G by 12. 55 by 2. Anyone else? What is the catch? Just now I gave you the formula. H is equal to P naught by rho G. So here, if your lift is going up, what will be the G effective? The gravity G effective will become G plus A. So here the new height H dash will be the new pressure 3P naught by rho into G effective. This is 3P naught by rho into G plus A. This is your 60 centimeters. So this is P naught by rho G, this is 75 centimeters. You're done. So just take P naught and substitute there. So P naught will be rho G 75 by rho G plus A is equal to 60. The rho goes off. 15 fives, 15 fours. That will be 15. G is equal to 4G plus 4A. So A is equal to 11G by 4. Yep. Check. 55 by 2. Is that clear, everyone? Easy one. You just have to take the G effective. All got this? So the pressure is changing, G is changing. So this is the formula, P by rho G. Next one. This is another good one. Let's say we have a liquid here. We got an air bubble here of radius r. As the air bubble comes outside, when it reaches the surface, its radius becomes 2r. Outside the pressure is P naught, density of water is 1000. Find the depth of the lake. Again, bubbles are small, I'm just drawing it big. In air, bubble doubles its radius. When it reaches the surface. Find the depth of the lake. Assume isothermal conditions. Isothermal condition meaning temperature is constant. I hope chemistry you guys studied gas laws. Boyle's law yaad hai na? If temperature is constant, PV is constant. That you have to use that. P naught ka value is given, Re Samyak. P naught ka value you know na? 10 power 5 Newton per meter square. Right, Arya. Try others. Yeah. See. So here, when you're reaching the surface, the pressure is P naught. Here, the pressure is P naught plus rho GH. Since it's an isothermal conditions, then P1 V1 is equal to P2 V2. So P naught plus rho GH into 4 by 3 pi r cube is equal to P naught into 4 by 3 pi 2r cube. So we get P naught plus rho GH is equal to 8 P naught. So H is equal to 7 P naught by rho G. That is 7 into 10 power 5. Rho is 10 power 3, and this is 10. So this is 70 meters. So when you ever go for diving, right, this is one of the things that they will teach you when you're in a diving school. Kabhi dekha movies mein and all, the hero is, stuck in some kind of thing. He's sinking. And when he tries to come out, right, the air bubbles come out of the mouth. Kabhi observe kya? So if you've ever been in a diving, right, let's say you're going for a diving. So you have an oxygen cylinder, you're at a depth of, let's say, 50, 60 meters, and then you're breathing inside. Now understand this, you're breathing air at a very high pressure, right? That is almost 7 times, 8 times the pressure. You're breathing at high pressure. So the air which goes into your lungs is actually a concentrated air. Now, let's say you take a deep breath, hold the breath, and you start coming out. What do you think will happen? That volume will become 8 times, isn't it? So your lungs will explode. So before that, you will lose your breath actually. So it's a very dangerous situation. So what happens, right, when you're diving and when you're coming to the surface, you have to keep releasing the air continuously out of your mouth as you're coming up. You just can't hold your breath and come to the surface. You're going to puncture your lungs. So that is one more thing. And at that high pressure, right, multiple things happen. You can't breathe your normal air. At high pressure, nitrogen starts getting combined with the blood. Normally what happens, right, when you're breathing, your oxygen and carbon dioxide, right, get absorbed by the blood. Carbon dioxide gets released, oxygen will be absorbed, nitrogen will do nothing basically. But at high pressure, even nitrogen will start getting absorbed by the blood, right? And if you breathe nitrogen at a high pressure and when you come to the surface, suddenly what will happen? Pressure has decreased, nitrogen will start bubbling from your blood. Kabhi aapne open kiya water bottle, this thing, Coke or Thumbs Up, when you open it, you get that carbon dioxide bubbles. So the nitrogen will start bubbling from your blood. Not a deadly condition, but you will be in extreme pain and you won't recover for 2-3 days. So in your gas cylinders, right, which they use for diving, they mix helium and oxygen. They don't use nitrogen. So those are special cylinders. You just can't put any cylinder and send people underwater for diving. So there, again, if you're just diving for 10, 15 meters, chalta hai. But if you're going deep diving like 70, 80, 100 meters, I think 50, 60 meters is the limit. People don't even go 100 meters is like too much. Yeah. So that is there. You have to get acclimated. You have to put you in a chamber and get used to all that stuff. So if you ever been to diving, you will realize. If you have ever been into swimming, and you will notice this, if you go deep into the pool, you actually start feeling something. Something is crushing you. But normally our pools are not that deep, right? 5, 6 meters. If you go to Dubai, I think they made a pool which is literally a full building size, very deep pool. So there. So let's see a question based on this. So we got a liquid here. Let's say you take a cylinder. It's a cylinder, open both the sides. So this is 50 centimeters on one side and 50 centimeters at the bottom. So the cylinder is half immersed. It is open at both the sides. And let's say the pressure P naught is 75 centimeters of mercury. I will keep it easy for numbers. And this liquid is also mercury. Then what you did, you sealed it on the top. So you sealed this container on the top. And then when you seal it, what will happen? Some air will get trapped inside P naught. And remember, this height is still 50 centimeters. There's no problem. And now you push it inside. Pushed inside by 25 centimeters. When you do this, now the picture looks a little different. Are you getting the whole scenario? You took an open pipe on both the sides. You kept it in the liquid, half out, half in, right? And then you sealed it on the top and then you pushed it in. So it is still sealed on the top. Now we observe the liquid level does not remain same. The liquid level actually rises inside. Right? So what is this X? This is 25 centimeters now, and the bottom is 75. Right? So you pushed it inside, or you can actually do the other way also. I can pull it outside. Either way it works. I think I should pull it outside. Pulled out by 25 centimeters. And we notice the liquid level does not remain flat. The liquid actually rises inside. So this guy is 75 centimeters and this is X. Getting it? So liquid level rises by X when the cylinder is pulled out. Find X. Assume isothermal conditions.
So that X is from 25 centimeter or 50 centimeter.
From the liquid level, Ray.
Okay, so
That is from the liquid level. Find X, assume isothermal conditions. Again, when the moment there's an isothermal condition, he's saying use PV is equal to constant. I hope the whole story is clear. You took a cylinder which is open on both the sides. You kept half inside, half outside, 50-50. It is in a mercury thing, and P naught is 75 centimeters of mercury. Now you sealed it on the top. So inside the pressure is still P naught. Now you pulled it out by 25 centimeters. And for some reason, the liquid actually didn't remain flat. It actually went up inside the cylinder. So by what amount did the liquid rise inside? So what exactly happened? Start from there. Let's see what is happening exactly. When you sealed the container, there was no problem. But when you pulled it up, you did something. You increased the volume of that gas. So that means the pressure cannot remain P naught anymore. So when you sealed it, the pressure was P naught, fair enough. But when you pulled it out, you made 50 into 75 volume increase. The pressure will decrease. It will be P dash, right? And at this level, we know the pressure is still P naught only because it is the same as the ground level. So P dash plus rho gx must be equal to P naught. Are you clear with that? That is the new pressure of the gas when you pulled it out by 25 centimeters. Are you guys clear why the pressure decreased? When you pulled it out by sealing it, you increase the volume, so pressure drops. Because the pressure decreased, the liquid actually went up. So then you're done. So P1 V1 is equal to P2 V2. So what is initial volume? Initial pressure is P naught, area into 50 centimeters is equal to the new pressure is P dash into area into 75 minus X. So P naught is how much? 75 centimeters of mercury, 75 rho G 75. Area will cancel on both the sides. This is 50. P dash will be P naught minus rho Gx. P naught is again rho G 75 minus rho Gx into 75 minus X. Rho G will cancel on both the sides. We'll get 75 into 50 is equal to 75 minus X whole square. So I can write P naught is equal to, what is P naught? P naught is rho G H, where H is 75 centimeters of mercury. Clear with this? So that way, that is the reason I gave 75. You get a decent numbers. So when you solve this, you'll get, it's a quadratic, you get two roots. You take 75. What do you get? 25 root 6 it seems. Check kar lena. You get a positive root and a negative root. You can't be positive. You can't exceed more than 75. So the negative root is the answer. Clear with this? There, not a tough one, but you should know what is happening there. When you sealed it and you pulled it out, you increase the volume. So pressure will drop. If the pressure inside decreases, the liquid will rise to maintain the pressure P naught at the base level. Clear this? Any doubts on this? So reverse, if I had actually pushed inside, the liquid level would have got depressed. It won't rise, but it actually goes inside. Any doubts on this? Yeah. Now let's see one more on this. I hope everyone knows the ideal gas equation, right? PV is equal to nRT. I hope that much is done in chemistry. So and let's do one more on this. This is another standard one. We have a tall container. This is filled with an ideal gas. Assume the temperature is constant everywhere. It's a tall container, meaning almost infinity. But we are assuming gravity is also constant. Assume uniform, even that's a tall container. The pressure at the bottom is P naught. The molecular weight of the gas is M. Find the pressure of the gas at a height h from the base. So if you start going up, what is the pressure as a function of y coordinate or height or whatever? Let's take this as y. Find pressure at a height y from the base. Let me take it as h maybe. Let's take y only, y looks good. Let's see how will you do this. So we have to use PV is equal to nRT. You should know that equation. Ideal gas equation you should know. So a little bit of ideal gas equation plus fluid mechanics. I'll help you a bit with the ideal gas equation. PV is equal to nRT. PV, number of moles, is nothing but mass by molecular weight. Mass by volume is density, so rho by mRT. There, you will need this relation. This is the relation between pressure and density. That means as you climb higher and higher, your pressure will change, so density also will change. So density is not constant. You can't use that equation, remember?
Sorry.
If your pressure, if your density is changing, that means you can't use that P naught plus rho H thing. There, you will need this equation. In case you don't know about the ideal gas equation, this is the thing which you need. Now try how will you do this. Try, take a minute more, then I'll show you. So what is the second equation? dP is equal to rho g dH. Remember the differential form? This is the differential form, right? If something is changing, this is what we have to use. And be careful here, H is measured from the top. But here you are measuring from the bottom. So therefore, dH will be minus dy. So dP will be minus rho g dy. And what is rho? Rho will be pressure into molecular weight by RT. Bring all pressure ka terms to one side. dP by P is equal to minus mg RT dy. Integrate on both sides. When you are 0, the pressure is P naught. When you are Y, pressure is P. That will be ln P by P naught is equal to minus mgy by RT. So P will be P naught into e power minus mgy by RT. It will be an exponential thing. Check it out. So as you go higher and higher, the pressure will keep dropping. It becomes 0 to infinity. You need to combine this ideal gas equation with this thing. So primarily, these are the two main things. dP is rho J dH, and this is the pressure. So you need ideal gas equation there to get the relation between pressure and density. So this is what happens actually. As you go higher into the atmosphere, your pressure density actually decreases. The air becomes thinner. Ever been to Ladakh? If you go there, the moment you get out of the plane, you will feel it. Immediately you will feel it. There, you get only around 60% of oxygen, 60-65% of oxygen on the ground level. So whenever if you're trying to visit Ladakh, right, the first 2 days, you're supposed to just sit in the hotel and get used to the climate. Your body does adjust. 65% you'll still survive, 65-70 around. Right? It takes around 2 days. You should not be moving around. After that 2 days, you can move around a bit. But if you're trying to do little heavy stuff there, then you need to wait for 15 days. So that is one problem whenever you're visiting Ladakh place. So when you go there, you have to sit for 2 days without doing anything. It gets boring. But once you come back from there, normal, right? Again, it will take a day for you to recover again because your body got used to that light air. It becomes again difficult to breathe denser one. Either way, it's a problem. Clear with this? I went there last year to run a marathon. Not a full one, but deadly place it is.
So did you feel like dying in that so low oxygen levels?
They call you 7 days before to get used to the climate. No, but it feels very bad, very bad. Meaning it's like a torture only. And that too, I'm not a professional runner. So I just run like 21 kilometers. That's it. So it's very difficult. Anyways, we'll see. Someday I'll run 42. Next thing. And that too, the worst part of that thing was the last 5 kilometers was a continuous uphill. That killed us all actually. वो छोड़ दो. People run 120 kilometers there. They have a special race called Silk Route, which is 122 kilometers. If you heard the in history, right, the Silk Route karke, that is where the trade used to go. That actual route you actually get to run. They start at night 7 o'clock. No, afternoon 3 o'clock they start, and you have to finish all the race by I think next day. I think night 7 or 6 o'clock. I guess you have to finish all the race by next day 5 p.m. You have to finish all the race in around 18, 19, 20, 22 hours. 122 kilometers. They're running in the entire night in the dark. And they reach a height of around 5,500 meters. And then they come down again. One of the toughest race. They select only like 70 people all over the thing. Only 70 people can run that entire track. It's called the Silk Route. Yeah, it's an experience to see those people, how they come running. So what is the Pascal's law? So this thing, right, the increase in pressure at a point is transmitted throughout the transmitted undiminished, so without decreasing, throughout the liquid and to the walls of the container. So what this thing says, right, in a liquid, if you try to apply pressure at one point, it just doesn't, it's not localized. It doesn't just stay there. It will increase the pressure everywhere in the system. I don't know whether you ever noticed this. When you're lifting something really heavy, right? Did you ever feel, there is a pressure on your eyes also? When you try to lift something very heavy, right, you will actually, the body may, right, the blood pressure rises. You can actually feel it in your eyes also. And this is a concept in the hydraulics also. Whenever you see this, did you ever see that, what is that thing called? Jackhammer. They break the roads and buildings with that big thing, isn't it? That brrrr karke, that machine thing. I think it's called jackhammer only. So they have a rod kind of like this and they hit it and hit it. This is actually a pneumatic drill. It is based on air pressure. Getting it? So the idea of this thing is, if you look at all your hydraulics, right? Or kabhi ye dekha BMC ka that the garbage wala truck. So you have that lift and that everything which puts inside. If you see, all these are based on hydraulics. If you see any crane, anything, that thing, right? They all are based on hydraulics. So the idea of this thing is, let's say if you have a pipe or something, right, and this is connected to the machine, I'll just give you a rough design. See, a hydraulic drill, right? It would look something like this. So you have this hammer kind of thing here. So this thing, right, the valves, so it is connected like this, and in the middle you have a valve here. Okay, so it is something of this sort. Again, I'm not doing it properly here, but something like this. So when the air enters from here, this thing pushes this, it will hit this, and this will go front. And then if you shift the valve this side, air will enter from here, this will pull it back again, this will come back again. So by shifting the valve front and back continuously, you can make this go front and back. I didn't draw it properly, but there's a mechanism like that. These are called pneumatic drills. Best example. Ever been to a dentist? You must have gone for sure. कभी ये देखा when the dentist is cleaning your teeth or drilling your teeth, right? Brrrr करके the sound comes. Did you observe? The dentist actually has an air tank inside the hospital, in that clinic. The dentist, right? The drill she uses actually is a pneumatic drill. She's using air pressure in order to control the speed of the drill. And you know how does she control? There is a pedal under the seat. She presses that pedal, just like your vehicle ka accelerator and decelerator types. So when she presses the pedal, the pressure increases and the drill rotates faster. Next time when you go to the dentist, observe that. You will hear that sound in the dentist ka thing. Yeah? It's an air tank which is filling it up. It's actually based on air pressure. So your dentist ka, all that equipment is based on air pressure, pneumatic drills. So there. So what this means here, right? Why all that? I can give another example. Did it ever happen to you? Let's say in your class, there is a bench and 3 people are sitting there. There is only place for 3 people. But one of your friend will try to come and push here and try to sit 4 people. Who feels the pressure? Does only the person in the corner feel the pressure? All 4 will feel discomfort, isn't it? So the pressure will be transmitted everywhere. If you ever been into a local train, you will understand this. In Mumbai, a local train, right, evening, when it is completely packed and there is not a single place to get inside, but still one guy will try to push inside and get inside. You know who feels the pressure? The entire compartment. Everyone, everywhere will get pushed. Everyone is getting crushed. So yeah, but since we are humans, right, there'll be still some spaces. It works out. But if it is an ideal case, everyone in the compartment will feel the pressure. So that's it. That's what Pascal law simply says. If you increase pressure at one point, it will not be only at that position, it will be everywhere. I'll show you something. So let me give an example. Let's say we have a container here. Let's say sealed container. So if you take a point here, A, and if you take a point B here, let's say this is height h by 2. And this is h. So pressure at A will be rho gh because it is sealed. And the pressure at B will be rho gh by 2. Now in this container, let's say you make a small hole. Now, the moment you make a hole there, in reality, the atmosphere pressure is acting only at the hole. But suddenly the pressure at A becomes P naught plus rho gh. The pressure at B also becomes P naught plus rho gh by 2. You're getting what I'm saying? Even though you increase the pressure at that one small point, the pressure will be transmitted everywhere. Everyone will feel that additional pressure P naught. So that's your Pascal's law basically. So this actually has a very interesting phenomena. One thing, they use this in hydraulics. They use this in pneumatic drills and everything. They are also used to, make some perfect spheres. Let me show you how would that look. Look at this.
I've come across a small.
So you can see this thing. Normally, now when you want to make perfect spheres, first they take some plates and they weld it up. It's like a polygon kind of thing.
Oh, video clip in various compilations on YouTube.
So they fill up these tanks with complete water, and the top, they put a small dynamite. So when the dynamite explodes, it generates so much high pressure, it pushes the whole thing uniformly. So something happens.
Showing a small explosion going off inside of a polygon-shaped sphere, which forced it into a round sphere. If it any user
Can you see how they became round? This is one of the best way to create a sphere. So when you increase pressure at one point, since the pressure gets transmitted equally in all directions, the best shape you can form is a sphere. So when you want to form big spheres, this is one of the technique they use.
lasts a few seconds, so I didn't know what the objects were or what was happening, but I really wanted to know. So I started doing some research.
So once you get the sphere, then they do this thing is in Singapore actually. So there's some art. You can use this in art museums. You can actually use this to make concave mirrors. So when you want to have this big mirrors, this is one of the thing you can create spherical surfaces. So yeah, that is one. And remember last time I was talking about the water jet rho a v square. So if you have a water jet, wait, I'll show you something else.
Recently,
There.
some friends of mine went to the
I
Gordon
think Utsa, you're asking how the dam looks there. Can you see this dam? It's almost straight, vertical, but look at the curve.
Dam in Tasmania, which is 126.5 meters.
126 meters of a dam that is. So you can see the walls are not exactly like a square plate. They make it a curve.
415 feet.
That design is pretty unique. It's self-sustaining. So all the dams won't be like the way I showed you. They'll be different. Then look at this. If you have a water jet, remember water jet ka force we studied rho a v square. If you can make the jet very thin and if you can hit it, you can use this as a cutting tool. It just cuts the lock like a hot knife under butter. This is called water cutting. So whenever you want to cut something, see when you weld something, what happens? It just will melt. So this is a pretty nice, thing to cut like pretty good shapes. You might think it is just water. If you put your finger, it goes off. That's a metal lock, huh? So, and someone actually did that experiment also.
Every time the water jet is running.
So what happens if you put a hand under a water jet now? We'll not put a real hand.
Weird primal urge.
So they created some 3 fake hands. There. They made some 3 fake hands which add similar strength to a human hand. And we are going to put these things. So don't try this at home.
See what kind of damage is done to these pattern on these. This poor specimen looks like he had fibromyalgia going up, guy. It was adjusting something on the jet and accidentally slipped and went. Yeah. Or you just, you've risked it all. You risked it all.
Yes.
Interesting. I wonder how that got out there.
Can you see what happened there? The entire bone came out.
Well, you'd be missing the tip of your finger. The bone would still be there. For the most part, it even took a little chunk out of your bone right here. But your flesh would...
There. So it's pretty dangerous. You know what most people think? Only water jet. Now what happens? It's not only water jet. When it is hitting at such a high pressure, first it penetrates your skin, it makes a hole. Right? And when you're trying to pull it out, imagine like this. Someone takes a knife and puts it through your hand, and then you're trying to pull out your hand. Your hand will literally get cut. That's how it feels inside. Then there is one more thing I wanted to show you. What is this one? There is that guy. I think it is there in thermodynamics, I guess, water vaporizing. It is there somewhere. I'll check it out. This is another. This we'll talk about later, but yeah, I think that's it. Okay, so that's a little about Pascal's law. So this is based on, we can actually create something called a hydraulic jack. Let me show you that. So this thing, right, they use it in garages and everywhere. So the idea is this: if you are bringing a car for repair and you want to, lift the car, not much, maybe you want to lift the car by 10 centimeters. So we use this machine. So one side you have a big area and one side you have a small area. So let's say we have a piston here, let's say area A2, and let's say we have a big piston here, let's say this area is A1. So idea is pretty straightforward. So it is filled with fluid here. So if you apply force F2 here, because of this, the pressure here will increase by F2 by A2. And this pressure will get transmitted from here to here. So this will push by delta P into A1. So this will generate a force F1, which is delta P into A2, A1. So we get F1 will be delta P into A1, which is F2 into A1 by A2. So this becomes actually a force multiplier. So example, if let's say A1 is 10 times A2, then you get F1 is 10 times F2. Means if I put 10 kgs on the right side, I can lift 100 kgs on the left hand side. So it's a force multiplier of 10. Getting it? But what is the catch? You can't get something for free. So if the force is more, something else should compensate. So here we conserve volume. So when you're pushing on one side, you actually don't go to the same height on the other side. If this side you push it by x1, then this side will go to by x2. So if you conserve volume, we get A1 x1 is equal to A2 x2. So yeah, I agreed, you get more force, but this will be x2 by 10. That means you'll get 10 times the force, but the displacement will only be 1/10. Are you getting this? So if you put 10 kg ka weight on the right side, and if you push it by 1 meter, on the left hand side, you can balance 100 kgs, but it will move only 10 centimeters. So you're actually compensating, you're getting more force by sacrificing displacement. So that means, are you getting any extra energy here? No, actually you are still conserving energy. If you look at the conservation of energy here, the work done will be F1 x1, right? Which is equal to F2 x2, which is constant. So you're not creating any extra energy in this system. So F into x will be constant. You'll get more force, but you're sacrificing displacement. Clear with this? So this is the concept of a hydraulic jack. So yeah. So that is one. So next class, when we catch up, we'll continue from here. We're going to do something called buoyant force. So that's again an important concept, Archimedes principle and all that stuff. So we will see again on Tuesday. So we'll wrap up with that. I'll see you guys again next Tuesday. We'll continue from here. And do remember, there's a test online till tomorrow. So make sure to give it. So any doubts, anything else, please stay back.